Bank of New York, and she'll tell us about economic modeling at the Federal Reserve.
Hi, everyone. Thank you for having me here today. My name is Rika, and I'll be talking about a new and exciting project that my colleagues and I have been working on and developing in Julia, extending existing functionality in our current repositories, DSGE.jl and statespaceroutines.jl. A bit of my background: I graduated from Brown University with a degree in mathematics and computer science, and have been working within the monetary research function at the Federal Reserve Bank of New York as a research analyst. As a fun aside, my particular team at the Fed has now converted all of our code basically into Julia, so we no longer have any main policy tasks that we do in MATLAB, and the dark days are behind us. Before I begin, I'm obligated to read the following disclaimer that the views expressed are my own and do not necessarily reflect those of the Federal Reserve Bank of New York, nor the Federal Reserve System, and any errors are on me. So with that, let us begin. Our motivation for this project is pretty simple. We want to be able to coherently model inequality, and we want to do so within a fully structural context. We also want to be able to ask questions in the nature of, when some event occurs in the economy, who is benefiting and who is suffering as a consequence? And what are the differential traits or asset holdings that differentiate the experiences of these two agents? We also want to be able to study the effects that known heterogeneity in society has on macroeconomic variables of interest. And by heterogeneity, I mean exactly that. People are different, they behave differently, and we're interested in the nature of how the distributions of various attributes manifest themselves in macroeconomic dynamics. Obviously, to the extent that heterogeneity does have an effect on these dynamics, as a policy and research institution concerned with things like accurate forecasting, pursuing optimal monetary policy, and understanding the past, we want to be able to produce the best models possible. And what I'll be discussing in this presentation is basically why most macroeconomic models currently in deployment at policy institutions are insufficient along these dimensions. And changing them to accommodate these objectives will prove to be methodologically and computationally quite challenging, requiring some divergence from what has been done historically. So, as a bit of a roadmap, in this talk, I will first provide a review of what dynamic stochastic general equilibrium, or DSGE models, actually are, before introducing the concept of heterogeneity and its relevance in studying macroeconomic dynamics, answering policy questions, and fitting macro and micro data. Along the way, I'll be explaining the short and limited history of estimating HA models in the literature, along with what exactly it is computationally about these models that has stalled their mass deployment to policy institutions' toolboxes in the past few years. Then I'll mention a bit about why Julia has been particularly compatible with the sort of work that we've been doing, and for this project in particular. Okay, so what is a DSGE model? Bit of a mouthful. For those of you unfamiliar, I'll start with a refresher on what this broad class of economic models actually are. To explain the acronym first, the D stands for dynamic, which just means that our analysis is time dependent. Consumers and firms face intertemporal decisions, which we model their expectations of the paths of these variables explicitly in the model. S is stochastic, so the economy is driven by shocks, which we have the capacity to identify via restrictions imposed by the economic structure of the model. This is because we permit the existence of random, unpredictable forces. For instance, you could imagine that political turmoil or a natural disaster could have an outsized effect on output growth for a particular quarter, but both of these forces would be very difficult and sort of excessive to bake into some model of the US economy. So instead, we take them to be as exogenous and being drawn from some distribution. And the GE stands for general equilibrium. This means we take into account the system as a whole, as opposed to just looking at a cluster of particular factors and how they interrelate. This means that we have the capacity to basically ask how a change in any part of the economy could have ripple effects into any other part. And DSGE models provide us with the ability to conduct both quantitative and qualitative analyses of the macroeconomy. we can conduct forecasts, we can interpret the probable relative strength of various shocks to cyclic fluctuations that we see in the data, and we can conduct analysis of optimal monetary and fiscal policy as a result. We also have the ability to perform counterfactual experiments, such as what would have happened to the path of inflation if the Fed had, for whatever reason, jacked up interest rates to 10% in 2008. And we can ask questions like, what if there had been a large negative productivity shock at the start of last quarter? And we have the capacity to do all of this because our model is fully structural. To start by explaining what heterogeneity is in these models, it's helpful to begin with a discussion of what the representative agent assumption is. So to explain how all this fits in, put simply, due to a variety of historical and computational forces at work, DSGE models have tended to make two key simplifying assumptions. That is, first, that aggregate consumption can be aptly captured by consideration of a single representative consumer, and secondly, that aggregate firm behavior is similarly captured by a single representative firm. In justification of this assumption, from an academic history perspective, past research seemed to indicate that the inclusion of heterogeneity didn't actually matter much for consideration of the dynamics of macroeconomic aggregates. So this would be things like aggregate consumption, aggregate investment, or output. In this sense, carrying around full distributions in the solution and estimation of DSGE models was considered to add a lot in terms of complexity, but not add much in the way of novel economic analysis. But as you might think, there are some issues with this assumption. So on a normative level, these models just absolutely cannot speak to inequality. There's no sense of a distribution of resources in an economy when you've announced that there's just one guy who lives in the US. Similarly, without relaxing the representative agent assumption, we can't conduct welfare analysis, which explicitly concerns itself with the question of who wins and who loses when there's some change in the economy. This makes many macroeconomic models unable to address questions of unequal growth. So for instance, who on the wealth distribution gains when there's a sudden boom in productivity, nor questions of differential income risk exposure during recessions. For instance, who gets hit the hardest and first when the economy suffers. Our models are mum on optimal fiscal policy when the operative welfare consideration is that of inequality. The other issue is one of just matching the world around us. So in the data, we just don't see the representative agent assumption borne out. As you might imagine, there is real heterogeneity in behavior of actors across the economy. The rich tend to save at far higher rates, which is a logical consequence of having far higher permanent income and wealth, and they tend to have far lower marginal propensities to consume. Additionally, there are several sort of puzzling implications of the representative agent hypothesis. To give a concrete example from the line of work that I'm in, there's this puzzle surrounding the monetary concept of forward guidance. So that is a representative agent model when the central bank announces some future change in interest rates. A representative agent model will tell you that this has a huge outsized effect on agent consumption decisions today, which is like pretty implausible and isn't really borne out in what we see in the world. So this kind of generally lends itself to a question of whether representative agent models are providing for us dynamics that we can believe or are sound. To give you a sense of what all of this actually looks like, you can see the structure of a representative agent model, representative agent DSGE model here. So goods producers, as the name suggests, produce consumption goods and can sell them to households. Households in turn supply labor and can choose, pay taxes to the government and can choose to hold treasury bills. Banks can offer loans to capital producers who have the ability to transform resources into investment, and the government then levies taxes and sells T-bills. Most of these interactions are then subject to shocks, like labor supply shocks, productivity shocks, and investment shocks. And at monetary institutions, you'll also generally be looking at new Keynesian models, which just means that you also include price rigidities. And this basically means that monetary policy is non-neutral in the short run. That is, the central bank can actually affect, since the central bank affects the nominal interest rate, if prices are sticky, then this actually passes through to the real rate and will affect the real economy. And central banks, prefer to believe in the non-neutrality of monetary policy. Yeah. So to introduce heterogeneous agent models. To address a lot of the concerns that we discussed earlier, we want to allow for agents to exist on a spectrum along various attributes. And we can choose to incorporate heterogeneity along really any dimension. So consumer income and wealth, asset holdings, age, productivity, education, risk aversion, or on the level of firms and business cycles. This list is by no means exhaustive. Heterogeneous agent models also solve a lot of the problems that we were discussing. They are far richer models and have implications for a far larger set of observables. We can discuss the distributional impacts of policies. We have more data on which to inform our parameters and test theories, and we can also paint far richer portraits of household portfolios. Additionally, we have the capacity to try to get model parameters to fit both macro and micro time series, like moments of cross-sectional distributions. And we can do this by, instead of considering a single number for this set of these attributes, we represent them as distributions. So you might choose to have a joint distribution over income and wealth, which might shift over time according to aggregate shocks and policy decisions. And then you can ask questions like, what is happening at a particular locality of this distribution for the agents that are living there at a particular time period? In practice and in our code, we model this distribution as a grid, and you can, in our code base, specify the fineness of this grid by inputs to the model. And as you can imagine, perhaps already, adding this layer of richness and choosing to include, carry around, and track the dynamics of this distribution can potentially be very costly in terms of like the computational task at hand. So one question that you might have is, why now? Why is the broader economic community only attempting to incorporate heterogeneity at this point in time? Beyond focusing on the normative question, that it's important to track distributional changes in the economy for its own sake, it's a question of policy and academic intrigue. Newer papers have also begun to cast doubt on the question of whether the representative agent model is actually describing the aggregate economy as well as those that do incorporate heterogeneity, as in they're not like a safe approximation. So in the first paper that's mentioned, it's determined that the mechanism by which monetary policy is actually transmitted to the economy across these two models can be distinct. In a representative agent economy, the story goes something like this. There's an unexpected cut in interest rates, and this is transmitted to consumption via the channel of intertemporal substitution. That is, the central bank lowers the interest rate, and you're more incentivized to spend money today because in the counterfactual, you would choose to save that money, accrue interest, and spend it later. And this direct effect is the dominant channel in a representative agent model that the central bank can affect consumption decisions of people in the real economy. Meanwhile, in a heterogeneous agent model, and one that they've managed to fit to actually deliver realistic distributions of household wealth and marginal propensities to consume, the general equilibrium effects actually far dominate this other effect. So by indirect, you can consider instead the channel of, after the central bank lowers rates, individuals want to spend more today, so demand for consumption rises, which means that firms suddenly need to have more workers because they need to be producing more because people want to buy more things, which means that if firms are hiring more people, demand for labor goes up, wages go up, and then people have the ability to, and then people have more income. And when you properly represent the distribution of agents along an agents' income, you'll see that approximately 30% of the US population, for instance, is usually income constrained, so they actually end up spending that money, and then a virtuous cycle continues. So in effect, these two models are just disagreeing, report totally different dynamics at play in terms of what the actual monetary policy transmission mechanism is. And this is very significant from the perspective of a monetary policy institution. Beyond this, another recent paper has shown that including heterogeneity in a model with borrowing constraints actually solves that forward guidance puzzle that we were talking about earlier in the presentation. So that is, in heterogeneous agent models, because the plurality of agents in the economy are income-constrained households, they're the ones who are supposed to be providing that initial aggregate demand stimulus that sets off the multiplier effect. However, these agents don't respond to an announced change in monetary policy in the future because they're already spending basically all of their income, which means that the size of that aggregate demand stimulus is actually far lower. So you don't see this outsized effect of the Fed just announcing a change in rates, which is far more compatible with what we actually see in the world. So lots of reasons to believe that heterogeneity is actually delivering better on the promise of providing forecasts of macroeconomic aggregates. And secondarily, the landscape of research is changing. So firstly, we're coming into better data sources, which previously had been a restriction in us being able to measure the behavior of people at lower sections of the income distribution grid. Secondarily, various current events like the financial crisis and rising inequality in the country have brought this to the forefront of policymakers' minds. And thirdly, most importantly, we are finally getting access to the sort of computational resources and algorithms that make the estimation and use of these models actually practical from a policy standpoint. So to give an example, a heterogeneous agent model that we recently estimated using previous techniques would have taken us like on the order of months, maybe like 6 months or so, and we're now able to do that in approximately 3 days, which is still a long time, I'd say, for most computer scientists in the room, but it's pretty good from the perspective of an economist. Yeah. So to give you guys a sense computationally of what is complicating our lives here, we need to look at how we actually represent these models mathematically. So to express the relationships and objectives between all those entities in the diagram that I showed earlier, we specify laws in the economy. These are very similar to, for instance, laws of physics. And then these laws can be written in the following system of rational expectations difference equations. By rational expectations, what I mean is just that agents correctly on expectation predict what the state of the economy is at time period t+1. So they can be wrong, so we have the opportunity to include expectational errors, but they're not systematically wrong. And this is a common assumption made throughout macroeconomics research. And that the vector of interest is that state vector, so ST, and it includes all endogenous and exogenous variables as well as expectational terms. So for instance, you'd have inflation, productivity, but then also people's expectations about inflation. And the epsilon term is then allows us to have those exogenous innovations, and the eta term are expectational errors. Yes, so you can see an example of these matrices included in our code base for the most part. If you're interested in checking out how this works, the EQ-cond or equilibrium condition files will have different solution methods that we use. So after you establish the set of rational expectations difference equations in canonical form, you need to get these into the form of something that we can actually work with. And you need to solve out basically those expectational terms. So at this point, depending on the nature of the model, for instance, if it's linear, nonlinear, discrete time, or continuous time, we employ different solution methods, for instance, Klein or Gensis, which converts this system of equations into a state-space representation of the economy, sans any expectations. So you guys might be familiar with this if you're coming from the background of engineering or physics. And the methods Gensis and Klein both solve multivariate linear rational expectations models, and I won't get deep into how these solution methods work, but if you're interested, you can check out our code base. So after we solve out the expectational terms, we're left with a series of matrices in state-space form, which enables us basically to conduct inference on the model while drawing on an expansive literature coming from statistics, econometrics, physics, engineering. And to refresh, for those of you who don't know, a state-space representation is basically composed of two main equations. The first being the transition equation, which describes the evolution of states across time periods, and the measurement equation, which is a mapping from model variables, potentially unobserved latent states, into things that we actually see in the economy, for instance, GDP growth or core PCE inflation. And then we treat that data that you'll see as a set of random variables, and the name of the game is basically just estimating that data. So we conduct inference on it using Bayesian methods. This also means that we can establish priors on theta, which could include basically any data that's not in our estimation, for instance, results from microeconomic behavioral studies, or any beliefs that the policymaker might have or econometrician in question might have over what those true values actually are. And obviously we can adjust the tightness of our priors as you like. It's a standard Bayesian approach, and you can see the syntax that we use for this in our code base. It's very pretty. Highly recommend. And finally, recognize that a state space representation is agnostic to whether or not whether a model is using a representative agent paradigm or a heterogeneous agent paradigm. So you would use this in either case. And thanks to multiple dispatch, if you're using our code base, you can simply call solve m on a model and get back the set of matrices and the transition equation, follow these steps, and then also get back the measurement equation. And from there, you can basically just run wild with whatever you want to do. You can iterate the transition equation forward, so you can forecast states in the future, and you can do like filtering, smoothing, conducting likelihood analysis, all that. So there are some performance concerns associated with this method. If we look at the model again, you'll see that anything that we might want to do really all rests on the length of that ST vector. The issue is that when we decide that we want to carry around the distribution, what we're basically doing is we're jacking up the size of ST from something on the order of like 45 states, which is considered a medium scale model, to something on the order of the thousands. And if you want to get any further precision in the model, you're basically resigned to using resigned to using even more states, like even above that like 1,000 level. So further computational issues that we've had is that you can't fully log linearize rational expectations equations, which also mean that that solution step becomes super non-trivial, both either in human time or use of automatic differentiation, because this is becoming like a really huge unwieldy partial differential equation. And additionally, every single time we solve the model, we need to every single time we compute the likelihood, we need to then reevaluate that solve step, which can then also jack up runtime to like somewhere on the order of like 10e6 of what we were the difficulty we were already having in the solve step. And additionally, there are a whole lot of matrix operations that happen in the Kalman filter, for those of you who are familiar, and these matrices are like massive, and we have to perform a lot of them by every single time we compute the likelihood, and then every single time period that might be included in our sample. So we have two general new requirements which deviate from standard macro estimation approaches. The first is that we need to be able to compute the likelihood really fast for a large state vector. And for this, we've built in functionality into our code base in case any of you have Kalman filters at home that you would like to take a look at and borrow from our methods, which involves the Chandrasekhar recursions, which in an instance where you have a super large number of states but a smaller number of observables, you can basically dump some of the runtime into making it an O of n y squared ns, as opposed to O of ns squared, where ns is the number of states and y is the number of observables. And this works so long as you don't change the transition and measurement state matrices are not time varying. And you can see an implementation of this in our state space routines package. And also it means that we need to be able to heavily parallelize everything that we're doing, because the likelihood computation has become super non-trivial. So something like Metropolis Hastings is just not going to work for our purposes. And for this, you can refer to my partner's talk, Ethan, who will be discussing basically what we do in terms of estimation of these models using sequential Monte Carlo. And finally, to sort of like provide a bit of a statement of, I guess, why Julia and why that's been helping us in particular. Firstly, just incredible speed improvements that we've seen. We use a lot of code from collaborators, and so while some of our comparisons like aren't perfect comparisons because we're not like optimizing their code at the same degree of fastidiousness as we're optimizing our own, we've seen complete dominance of the same functionality in MATLAB, and in many instances overtaking FORTRAN code, which has been pretty impressive. We've also found that the use of being able to specify type hierarchies and then intelligently use multiple dispatch has reduced this like just net length of number of lines of code in our code base by an insane amount, and has also improved forms of readability and interpretability by people who aren't perhaps coming from a computer science background, but are rather economists who just want to be able to look at our code and actually understand what it's doing on an intuitive level. And it keeps you also honest by constantly referencing what the types of objects should be, so people can't switch up and make alpha into a vector when previously it had been a float and confuse everybody during the debugging process. And similarly, parallelism has proven to be incredibly easy to pick up, very easy to explain to, for instance, interns, and has enabled a lot of members of the economic community to collaborate with us in the development of our code base in a way that previously would have required a much higher upfront cost in terms of learning the language. And also automatic differentiation is quite fast. Yeah, So on the horizon, we will be rolling out this heterogeneous agent functionality. You can technically already implement heterogeneous agents using our code base in the event that you wanted to, but we've already implemented several models. We're just running final tests on them, and we'll be putting those out in terms of examples that you guys can follow should you want to. And we'll also be expanding features for the inclusion of continuous time solution to these models, as opposed to just discrete time, probably coming up in around the next year or so. So lots of things to look forward to. Thank you for having me.
Okay, so we have plenty of time for questions. So go ahead. Yeah, please go ahead. Yes, if you could just repeat the question.
Yeah, you got it.
So where do you get the data to test this? One of the things I've always heard is that economists complain that they don't have enough data to test on, whereas physicists can just generate it out of the air.
Yeah, certainly. So one of the things that our team is actually advantaged in is that the observables that we include, as you saw back in the measurement equation, include quite precisely well-measured series. So we're taking things like GDP, core PCE inflation, stuff that's being put out by the Federal Reserve Bank of St. Louis for the most part. So while this might be true of, I guess, people in other disciplines of economics, I'd say the data that we're using tend to be quite clean and reliable.
One quick question is whether you've thought about using GPUs. Another question is whether your rational expectations, I guess I'm not an economist, but I at least have a bit of a hint that people are not always rational. So I just wonder, are there ways in which they're predictably irrational that could be modeled? I'm just kind of curious if you could comment on that just for fun.
Yeah, so it's certainly a simplifying assumption. Well, okay, first to answer your first question, we certainly have thought about using GPUs. We have a finite budget, and there's, I guess, some complications security-wise with like largely extending our computing apparatus, but it's definitely something that we've talked about and considered, and perhaps someone beyond my time will have the benefit of being able to learn how to like optimally code Julia for GPUs. To answer your second question, perhaps this is an issue you should take up with like the broader economics literature. I would say that by and large, it doesn't, like, people have experimented with different forms of models wherein people are like systematically irrational, but I would say for the most part, this is not insofar as you can still include kind of randomized measurement error, this largely isn't the limiting factor in being able to properly model a behavior in the economy. And also to the extent that we're just basically believing that the models that we think are kind of the models that like drive the functioning of the economy, we sort of believe that the average person similarly would believe these dynamics to also be true. So like to the extent that we're epistemically constrained, like other people, like this epistemic constraint would just be sort of borne out in the likelihood evaluation of the model. Yeah.
Thanks. I actually have two questions. Mm-hmm. Number one, how often do you update your model? And number two, is your model actually get used by the Fed, and how does it affect the decision-making process?
Yeah. So we will re-estimate our models approximately every quarter with new releases of data. And we're constantly in the development process of new models. So we have approximately like 20 that are floating around within our code base that we make adjustments to and will compare against each other. And we do actually use these models. We publish forecasts as well as shock decompositions on the Liberty Street Economics blog. And like all of the work that we do and all the work that all people on the research floor of the New York Fed do get composed and compiled and, used within the policy decision-making process to some extent, though I can't really talk about that.
All right, thank you.
Hi, I have a question actually about how you approach to modeling. So when you have those heterogeneous attributes? Do you discretize space, or you represent this as a continuous function, but which is just controlled by a finite number of parameters?
So we've experimented with both. One of the things that we did was we would use like a discretization where we would bin people with the assumption that people who are within some like epsilon of one another behave largely pretty similarly. And but we also have some functionality that we've been exploring that like views these distributions as being continuous, and the solution methods for those are a bit different. But those I think are not going to be released within like the same time frame. Yeah.
Okay, thank you.
Yeah.